welcome to the lecture series on mathematical methods and its applications. So, we have already discussed Fourier series. We have seen what Fourier series are and how we can solve some problems based on that. What are properties, what are convergence properties of Fourier series, that also we have seen, and also the complex form of Fourier series. Now, Fourier integrals, what Fourier integrals are and why they are important, let us see. So, if we have a periodic function f x which is defined on a real line R, then f x can be represented by a Fourier series that we have already seen, okay, which is given by a naught by 2 plus summation a n cos n pi x by L plus summation b n sin n pi x by L, that we have already seen. If f x is not periodic, suppose f x is not a periodic function, then it cannot be represented by a Fourier series over an entire real line. If we want to express a non-periodic function by a Fourier series, then it is not possible. However, f x may be represented in an integral form. Okay. How? Let us see. Now, first of all, suppose f x have the following three properties. F is piecewise continuous on every interval from minus L to plus L. F is absolutely integrable on x axis, that means integral from minus infinity to plus infinity mod of f x converges, that means this value is finite. Integral minus infinity to plus infinity mod of f x dx value is finite. And for every x belongs to R, f x has left and right hand derivatives. So, first of all, let us suppose the function f x is periodic, okay, and satisfy these three properties. Okay. Again, suppose f x is a periodic function with period 2L defined on interval minus L to plus L, satisfy the properties P1 to P3 which we have discussed, then it can be expressed by a Fourier series in this way. Okay. Basically, we derive the Fourier integral from the Fourier series itself. Okay. We have the Fourier series like this, we already know this, f x equals to a naught upon 2 plus summation a n cos n pi x upon L plus b n sin n pi x by L. So, this is a Fourier series expression and is varying from 1 to infinity of function f x. Okay. Where a naught is given by 1 upon L integral minus L to plus L f t dt. A n is given by 1 by L integral minus L to L f t cos n pi t by L into dt, and b n is given by 1 by L integral minus L to plus L f t sin n pi t by L into dt. So, these are expressions. Okay. Now, let us substitute these expressions over here. Okay. So, what we will obtain? F x will be equals to 1 by 2L integral minus L to plus L f t dt plus summation n varying from 1 to infinity. A n is nothing but 1 by L integral minus L to plus L f t cos n pi t by L into dt into cos n pi x upon L, okay, plus summation n varying from 1 to infinity, again 1 by L integral minus L to plus L f t sin n pi t by L into dt and whole multiplied by sin n pi x by L. Okay. Now, let us suppose let omega n is n pi by L. Okay. So, what will be delta omega? Delta omega is omega n minus 1, which is nothing but n pi by L minus n minus 1 pi by L, which is pi by L. So, let us substitute these terms in this expression. Okay. So, what will be f x? What f x we will obtain? So, f x will be nothing but is equal to, now now this 1 by L is nothing but delta omega by pi. So, it is delta omega by 2 pi integral minus L to plus L f t dt, okay, from this expression. Now, plus again this 1 by L will be nothing but pi upon delta omega upon pi from this expression. So, 1 upon pi will be outside, 1 upon pi will be outside, summation n varying from 1 to infinity minus L to plus L f t cos, and pi n pi L by L is nothing but omega n t, okay, into dt and whole multiplied by cos omega n into x into delta omega. Okay, delta omega by pi is here instead of this. So, delta omega is here, and similarly plus 1 by pi summation n varying from 1 to infinity integral minus L to plus L f t sin omega n t into dt and whole multiplied by sin omega n x into delta omega, because pi n pi L by L is nothing but omega n. So, it is omega n x into delta omega. Okay. Now, let L tend to infinity, because we want to expand the function over the entire real line. Okay. We want to expand the function over the entire real line. That is why we are tending L to infinity. So, as L tends to infinity, of course, minus L to plus L interval will tend to minus into plus infinity, that is over the entire real line, and delta omega will tend to 0. Delta omega is nothing but pi upon L, and as L tend to infinity, this will tend to 0. Okay. So, and function f x is absolutely convergent, that we have already assumed. Okay. So, this term, so this integral when L tends to infinity is finite and delta omega tending to 0. So, the first term is tending to 0, because delta omega tend to 0, and as L tend to infinity. So, this value, since is absolutely convergent, absolutely converges. So, this value is finite. Finite into 0 will be 0. So, first term is 0, and this will sum up as Riemannian sum, because L tends to infinity, and this is delta omega which tend to 0. So, this sum up as Riemannian sum. So, this will be nothing but 1 upon pi integral 0 to infinity, okay, 0 to infinity integral minus infinity to plus infinity f t cos omega t into dt whole with cos omega x into d omega plus integral 0 to infinity integral minus infinity plus infinity f t, it is sin omega t into dt and whole multiplied by sin omega x into d omega. Okay. Because L is tend to infinity, okay, and delta omega is tend to 0. So, this will be sum up as Riemannian sum. So, which is given by 1 upon pi integral 0 to infinity minus plus infinity, this term plus this term. So, that is what we have given the PPT also, that this resemble as a Riemannian sum of the definite integral as L tends to infinity. So, this will give this value. Now, here if we take this as a omega, because it is a function of omega, and this as b omega. So, what will be fx? Fx will be nothing but 1 upon pi times integral 0 to infinity a omega cos omega x d omega plus integral 0 to infinity it is b omega sin omega x into d omega. So, that will be this expression where a omega is nothing but minus infinity plus infinity f t cos omega t dt and b omega is nothing but minus infinity plus infinity f t sin omega t into dt. So, this is what the Fourier integral is. I mean integral representation of a function f x. Okay. Fourier integral representation of a function f x is given by this, where a omega is this and b omega is this. Okay. So, we expand the function over the entire real line by assuming that L is tend to infinity. Okay. So, this is how we can obtain this thing. So, this is called Fourier integral of f x. Now, suppose f x satisfies the properties p 1 to p 3, okay, which we have discussed. Then the Fourier integral of f x converges to f x at a point of continuity, the same as in Fourier series. This we have also discussed Fourier series also. The same follows in Fourier integrals also, that if it satisfies some properties p 1 to p 3, then the Fourier integral of f x converges to f x at a point of continuity, and at a point of discontinuity it converges to the average of left hand limit and right hand limit at that point. Okay. Now, let us try this problem now. We want Fourier integral representation of this function. So, we know that the Fourier integral representation of function is given by this expression, f x is given by this expression, a omega is given by this, b omega is given by this expression. Now, their function is what? Function is defined function is 1 when mod x is less than 1 and 0 when mod x is greater than 1. Okay. So, this is the function. Now, we want Fourier integral representation of this function. So, this function is defined over the entire real line. So, we want the Fourier integral representation of this function. How can we find it? So, we first find a omega and b omega. We substitute the values of a omega, b omega over here. So, that will give the Fourier integral representation of this function. So, what is a omega? Let us find a omega first. What is a omega? From here a omega is minus plus infinity f t cos omega t dt. Now, it is defined from minus 1 to plus 1, okay, is 1. So, minus 1 to plus 1 is 1, otherwise it is 0. So, it is cos omega t dt, and cos omega t is an even function. So, it is nothing but 2 times 0 to 1 cos omega t dt, and it is equals to 2 times sin omega t upon omega from 0 to 1, which is nothing but 2 sin omega upon omega, because sin 0 is 0. Okay. Now, what is b omega? B omega will be nothing but again minus infinity plus infinity by this definition f t sin omega t into dt, which is equals to minus 1 to plus 1 sin omega t into dt, because from minus 1 to plus 1 it is 1 and it is an odd function, so this is 0. So, we have computed both a omega and b omega, and the Fourier integral representation of a function f x is given by this expression, as we already know. So, this will be nothing but 1 upon pi integral 0 to infinity. Now, what is a omega? Is 2 sin omega cos omega x upon omega into d omega. B omega is 0. So, that will be the Fourier integral representation of this function f x. Okay. Now, we can also write this function as 0 to infinity 2 sin omega cos omega x upon omega d omega, which will be equals to pi times f x, and which is equals to pi, we multiply simply that by pi when mod x less than 1 and it is 0 when mod x greater than 1. Okay. This 2 you can also bring here, pi by 2, so it is pi by 2. And what happens when x is 1? When x is 1, so it is discontinuous. So it converges to average of left hand limit and right hand limit, which is nothing but what will be f1? f1 will be nothing but half of f1 minus plus f1 plus. So that will be nothing but 1 by 2 1 plus 0. So that is 1 by 2, and you have to multiply pi by 2 also. So that will be pi by 4. Okay. So in this way you can find out the value. The same you can find out when x equals to minus 1 also. When x equal to minus 1, we have the same value. It is x equal to when x equal to plus or minus 1. Okay. So, so this integral is equal to basically this integral. Now, we have to find out integral 0 to infinity sin omega upon omega d omega. So that will be nothing but you substitute x as 0. Okay, it is a function of omega. So you can arbitrarily choose any value of x. So when x is 0, so this is nothing but so you can substitute both sides as 0. So it is 0 to infinity sin omega upon omega d omega is equals to pi by 2 f0, and when it is 0, when f is 0, it is 1, so it is pi by 2. Okay. Or you can directly see from here, when x is 0, value is pi by 2, value of this expression is pi by 2. So you can easily see that this value when x is 0. Okay. In fact, when you put x equal to say half, when you put x equal to half, so when x equal to half satisfy this expression. So when x equal to half, the value of that will also be pi by 2. So you can easily find out under different values of x, the value of this expression is nothing but this expression. Okay. Now let us try to prove this, that this is equal to this expression. So how we can prove this? This is nothing but Fourier integral representation of function f x. So what is the Fourier integral representation of function? So what is the expression? It is 0 to infinity. It is cos pi omega by 2 into cos omega x upon 1 minus omega square d omega is equals to, it is given to you pi by 2 cos x when mod x is less than pi by 2 and 0 when mod x is greater. So we have to prove this. Okay, we have to prove this. So what is the Fourier integral representation of function f x? Is nothing but 1 upon pi times integral 0 to infinity a omega cos omega x dx cos omega x d omega plus integral 0 to infinity b omega sin omega x into d omega. Okay. Is it so? Fourier integral representation is into d omega, that is the same thing, and here it is dt. Okay. Now what is a omega? A omega is minus plus infinity it is ft cos omega t dt, and b omega is given by minus plus infinity ft sin omega t dt, that we already know. Now, if we compare this with this, so what will be a omega? So, it is pi fx, which is equals to, if you compare this by this, so cos omega x ka coefficient is simply a omega. So, we can simply say that a omega is nothing but cos pi omega by 2 upon 1 minus omega square, and b omega is 0, because there is no term of sin omega x. Okay. And this integral 0 to infinity a omega cos omega x dx is nothing but pi times fx, which is equals to pi by 2 cos x when mod x is less than pi by 2, and 0 when x is mod x is greater than pi by 2. So, this implies fx is cos x by 2 when mod x is less than pi by 2, and 0 when mod x is greater than pi by 2. Okay. So, you take this fx, and try to obtain the value of a omega. If you obtain a omega as this, that means we have proved. Okay. Anyhow we have assumed that this is true. Okay. Assuming this to be true, we have find out the coefficients a omega and b omega, and we have find fx. For this fx, if a omega comes out to be this, that means we have proved. Okay. So, what will be a omega for this fx and b omega? A omega should be this, b omega should be this. So, what will be a omega? A omega will be given by minus infinity plus infinity ft cos omega t dt. Now, it is given by fx is defined like this. So, from minus pi by 2 to plus pi by 2, it is cos t upon 2 into cos omega t dt, which is nothing but it is an even function. It is 2 times by 2 0 to pi by 2 cos t into cos omega t dt, which is equals to, now 2 cancels out, multiply divide by 2 again 0 to pi by 2, it is 2 cos a cos b, which is nothing but sin a plus b plus sin a minus b. It is equals to 1 by 2, integral of sin is minus cos. So, put minus outside, put minus 1 outside. So, it is cos of 1 plus omega t upon 1 plus, okay, both will be cos, sorry, cos a, 2 cos a cos b is nothing but cos a plus b plus a cos a minus b. So, it will be cos, and minus is not. So, it will be sin and plus sin 1 minus omega t upon 1 minus omega, and t varying from 0 to pi by 2. So, this will be nothing but 1 by 2, it is sin 1 plus omega into pi by 2 upon 1 plus omega plus sin 1 minus omega into pi by 2 upon 1 minus omega. Okay. Now, when you simplify this is nothing but 1 by 2. Now, sin 90 plus theta is sin theta. So, that is sin pi by 2 omega upon 1 plus omega. Again sin 90 minus theta, no, sin 90 plus theta is cos theta, sorry, it is cos theta. So, it will be cos theta, again here it is cos theta. So, this will comes out, this cos pi omega by 2 will come out, and it will be nothing but 2 upon 1 minus omega square. So, 2 cancels out. So, this will comes equal to this cos pi omega by 2 into 1 upon 1 minus omega square. Now, when you compute b omega must be 0. When you compute b omega for the same problem, so b omega will be nothing but what? Minus infinity plus infinity f t sin omega t dt. Now, it is nothing but minus pi by 2 to plus pi by 2. It is cos t by 2 sin omega t dt. Now, it is an odd function, so it is 0. So, hence we have proved, because we have obtained that a omega is this and b omega is 0 for this function, that means this results hold. Okay. So, we have shown the result. So, this is how we can find out Fourier integral representation of a function f x. Okay. So, thank you.